Hello. Today I'm going to talk about electromagnetic radiation and the photoelectric effect. So we want to introduce the electromagnetic spectrum, and the reason we're doing this is because we're still studying the early atomic structure and some of the experiments that led to our understanding of the atom. And one of those is going to involve light and how light interacts with the atom. So what we have down here is the electromagnetic spectrum. And the light that we see, the visible light we see, is a portion of this little portion right here, visible light. Those are all the colors that we see. We can't see anything else on this spectrum. Some other creatures can see ultraviolet light or infrared, but we only see this visual portion. Now we have machines that can detect all the rest of these: gamma rays, X-rays, microwaves, radio waves, TV waves, all those kinds of things. Now, all right, so what defines light as having wave-like properties? So there's two things that are going to define it as having wave-like properties. First is wavelength. Now wavelength is the distance from the top of one wave to the top of the next wave. So this distance here, it's measurable. That is our wavelength. The other wave-like property is frequency. And frequency is how often a wave passes through a particular space. So if we take the same distance and we put it over here, we'll say it's like about this distance. Which one has waves passing through it more regularly? Well, it's gonna be this one, because there's many more waves that pass through this spot than there are over at this spot. This has a higher frequency. This has a lower frequency. This one has a longer wavelength. These have shorter wavelengths. Okay, so let's see, what's an example of a long wavelength? Well, we can just look here. The increasing wavelengths are all the way over here. So what are examples of those? Radio waves, microwaves. These are things that have long wavelengths. And then frequency. What's something that has high frequency, like an example of that? Well, if I look at my picture here, the highest frequency goes this direction. So my high frequency waves are gamma rays or X-rays. There's also something that we can quantify that has to do with energy in the waves. And we can see again that the amount of energy increases as you go to the left. So, which ones have high energy on here? What are examples of stuff that have high energy? X-rays and gamma rays have high energy, especially when you compare it to low energy stuff like microwaves or radio waves, or even the waves that we use for cell phones. Okay, those are low energy, and these are high energy. Now, the reason we're studying this is because light will interact with electrons in a very specific way. And in the early 1900s, this gave us some information about the structure of the atom. All right, let's look at this next page. We're going to go a little further. So in this image, what we see is we see light coming in at a certain frequency. It's hitting this metal plate. And when it hits these electrons, some electrons are emitted. They're given off. So in the early 1900s, scientists observed light interacting with metal, and they found that when this light hit the electrons, they were emitted, right? This is called the photoelectric effect, okay? So when these light cause the electrons to be emitted, photoelectric effect. But what they didn't expect is that only certain frequencies of light would emit the electrons. What they thought was that any type of light, anything on the electromagnetic spectrum would be able to cause this photoelectric effect to happen, these electrons being emitted from the metal. But it didn't. Only certain frequencies. And that was a bit of an unexpected outcome. So then they had to figure out, okay, so what is happening here? So the next stage is to go into this a little further. And they started looking at different frequencies, measuring them. And at low frequencies, so this is light like radio waves. If it was low frequency, nothing happened. There was no electron emitted. But with high frequency, both of these are examples of high frequency light, then they did get an electron being emitted. Now, if that is true, which it was, that's what they observed, is that what they would expect if light only had wave-like properties? No. If it only had wave-like properties, then all light would be able to eject these electrons. So what scientists discovered, and actually Einstein was part of this, he actually won his Nobel Prize for the work he did on the photoelectric effect, not on some of his other work that would come later on. But as they experiment a little bit more, they say that light not only has wave-like properties, which is right here, but light also has particle-like properties. So light acts both as a wave and as individual particles when it interacts with material. And this particle of light, in this case, when we describe it as a particle of light is called a photon. All right? So we'll continue from this. I hope this helps.